We will now be starting chapter 3, which is all about limits. Please note that our main text has a very quick introduction to limits, so I wanted to make a very thorough explanations and have lots of examples, so we will be using a supplemental text for this particular chapter, which is why in the notes it's called chapter 3a. So look at the blackboard for the supplementary textbook. Today we will talk about just the introduction to limits, informal definitions, and some very basic notation and calculations. So this is what I call a very informal definition of a limit. It essentially comes from the word limit itself. In real life, when we hear the word limit, we associate it with something that one approaches, something that is kind of like attained as something, right? So for example, a speed limit. It's something you want to come as close to as possible. So if the speed limit on the road is 50 kilometers an hour, you don't want to be driving 35, and you also don't want to be driving 75. You want to be as close to 50 as possible. You could be driving 48, or you could be driving 52, and sometimes your actual odometer won't be able to tell you with that much precision what you're driving, what your actual speed is, but you want to be as close to the limit as possible. And that motivates exactly what a mathematical limit is. So the very informal definition is that the limit of the function is the y value that it approaches as x approaches some specific value. So an x value will be specified for you, and you will have to calculate the y value that the function approaches as x gets closer and closer to the pre-specified point. Let's take a look at our very first example here. Find the limit of a function y equals x squared as x approaches 2. So we're given the value that x will approach, it's 2. Let's mark it here on the graph, for example. So this is the value of x that I'm going to try to stay close to. Finding the limit means I have to find that as x is around 2 or as close to 2 as possible, what does the corresponding y value on the graph approach? Right? This is a nice simple function, so the answer here is pretty clear just from the graph itself. If x is really, really close to 2, then I expect that my y value is going to be really, really close to 4. That's how one can justify it from the graph, but we don't always have graph readily available. Let's think about what would we do if we had to plug in numbers. Now, I must warn you that plugging in numbers will give you great intuition about some limits, but it will fail miserably sometimes. So while you can do that, this is by no means a foolproof approach, which is why we're going to spend quite a bit of time talking about analytic and formulaic techniques to actually calculate limits in a much more precise ways. Before we start plugging in numbers, we have to wonder what kind of numbers are we going to plug in. So as x approaches 2, what does that really mean? So x has to be close to 2. Does it have to be close to 2 and less than 2? Or does it have to be close to 2 and bigger than 2? This doesn't specify that, so we actually have to consider both cases. So let's plug in some numbers here. So my table here will specify the x values that are closer and closer to 2 but less than 2, and that are closer and closer to 2 but are bigger than 2. These are the x values that approach 2. How do we calculate the y values that correspond to those? Well, our function is given here, y is x squared, which means that to find the corresponding y value here, I just have to take the corresponding x value and square it. Okay, you can try it for yourself on a calculator, but I have the table filled out here for us. So when x is 1.9, y is 3.61. When x is 0.199, so even closer to 2, y is 3.96. When x is even closer to 2, 1.999, y value is 3.97. Okay, so of course you can continue doing this for a while. Same on the other side, but we can clearly see the trend, and that is that as x's approach 2, y approaches 4. Now there are two cases that we're seeing here, right? So once again, it can approach but be less than 2, or it can approach but be bigger than 2. And those are actually the two cases that we will distinguish. So this, we will say x approaches 2 from the left, because it's physically on the left of the number line. In this other case, we will say that x approaches 2 from the right. Okay, and again, it's easy to see on the graph what that really means. If this is my 2 right here, then approaching from the right means that my x values are close to 2 but bigger than 2. Approaching from the left means my x values are close to 2, but less than 2. Now, because mathematicians are lazy and we're going to do this approaching from left or right a lot, instead of saying approaching, I'm actually going to use the arrows. So the mathematical notation for x approaches 2 from the left is x goes to, arrow, 2, and then to say that it's from the left, I'm going to use a little minus in where the power would normally be. Similarly, x approaches 2 from the right will have a little plus, signifying that it's close to 2, but a little bit bigger than 2. Okay, so we can say here that the limit as x approaches 2 from left or right seems to be going toward 4. Now let's take a look at not very informal, but just informal definition of a limit that will also introduce a very useful notation that we can use for the limit in order to save us from always writing as x approaches to the limit is, and so on. So my function here is f of x. The number x is approaching is a, and L is the limit itself. The notation, this notation, limit, we read it as this, limit as x approaches a of f of x is equal to L. So the word limit is on the outside. The function is the one that we're using. This specifies what the x value is, and this specifies what the corresponding y value is of the corresponding limit. So going back here, just for practice, on the left here, we had that the limit then as x approaches 2 from the left of our function, which was, again, remember, y equals x squared. So of x squared is equal, we decided that it was in fact approaching 4. And similarly, on the right, we can say that the limit as x approaches 2 from the right of our function was also equal to 4. Okay, so this is just how we use the notation. Now, this very informal definition is also useful in the sense that we can justify what some limits are going to be. If the function is somewhat nice. What it means to be nice, we're going to get to in a little bit. But this describes what the real meaning of the limit is. It means that the values of f of x can be made as close to the limit value as you want, but taking x sufficiently close to the chosen value. So for example here, I can make the y value be as close as I want to 4 by taking x's to be as close as needed to 2. Okay, let's see if we can, without graphing anything, if we can justify ourselves what a given limit would be. So here the limit is, as x goes to 0, of 2 to the power x plus 3. Okay, let me rewrite this just in a bigger font. So we read this as limit as x goes to 0 of 2 to the power x plus 3. I want to write it slightly bigger because I'm going to draw arrows and things like that around it. Okay, so the limit specifies that x goes to 0. But I don't know what this function goes to, and that's exactly what the question is asking. But as x goes to 0, I can denote this a little bit here, right? This x goes to 0, which means that x is going to be really, really close to 0. It could be a really, really small negative number, or it could be a really, really small positive number, but no matter what, it's going to be really, really close to 0. If you would like, pause the video here and plug in some values into this function where x is really close to 0, just again to see intuitively what the limit would approach. Now, if x is really, really close to 0, so I'm taking a very small positive or negative number, then what does x plus 3 approach? So this whole thing. If I'm adding a very small number to 3, then the sum will be very close to 3. Okay? And then what I have overall then is that I have 2 to the power that is really, really close to 3. So overall, I'm going to have 2 to the power 3 in the limit, which is, of course, 8. Okay, so this is the way that you can justify it out. Again, functions have to be nice and create no problems like division by 0 and things like this. We will learn how to deal with those shortly. But if you're just sort of plugging in your head or justifying what happens as x approaches a certain value, then you can intuitively understand what the limit value will be as well. Now, this is an informal definition, and this, in fact, is the definition that we will mostly work with. This definition, in many ways, is the original non-rigorous definition because that was the definition that was used by Leibniz and Newton when they invented calculus in the 1800s, in the 1700s. So those ultimate ratios are not actually ratios of ultimate quantities, but limits which they can approach so closely that their difference is less than any given quantity. So it's talking about how you can approach something infinitely closely. Now, this non-rigorous definition was not actually enough for development of some mathematics and particularly concepts in physics and things like elasticity. So over 100 years later, Cauchy, Weierstrass, and Bolzano came up with a much more mathematically rigorous way to specify what limits are. This is not a definition that we will work with, but I wanted to show it to you anyways and to show on the graph what it actually means, because graphically it's really easy to understand. I should also point out that if you have a minute, you really should look up some of the lives and biographies of these incredible men. So Cauchy was a French mathematician. He's in fact one of the 72 names that are inscribed on the Eiffel Tower as the biggest French contributors to science. Weierstrass is a German mathematician. One of the interesting things about him is that he was a great supporter and mentor of the first female mathematician PhD, which was Sofia Kovalevskaya. And Bolzano was an Italian mathematician. He's also a very interesting figure. As opposed to Cauchy, who was known to be a terrible lecturer, Bolzano was actually ridiculously popular with students to the point where he started lecturing in disciplines that were not his own. And he held very controversial views at the time that money should not be spent on warfare, but rather the government should spend more and more money on education and social systems, which those controversial views eventually cost him his job at the university. And we can see that some countries still struggle with being able to divert some money from warfare to education. Now, let's go back to the limit definition to see what this actually says. So it's easiest to understand graphically. So if I have a little graph here of some function, I'm not going to give you the actual function. I'm not interested in the definition itself. What this is saying is, if I have this a, some value for x that I'm trying to approach, and my eventual limit, so let's say this function is nice and smooth, so my eventual limit is here. What this is saying is, we can play the following game. You can tell me how close you want to be to L, and I will tell you where you have to start on the x-axis to be able to get that close to L. Okay? That's all this very complicated looking and very notation heavy definition is saying. This is very useful for things like if your x-axis, for example, is time and your y-axis is, for example, some kind of amount of medication in your system, then you can think of when do you have to re-administer a medication dose. You know how much drug in the system of a patient you'd like to have when you want to re-administer, and then the x-axis will tell you when when a new dose has to actually be administered, right? So again, you tell me how close you want to be to L, and I will tell you which x values will land you there. That's all that the actual definition of limit says. But again, the rigorous definition we're not really going to work with more than just past this graph, so we're not going to spend too much time on it. The two important nuances about limits that we will have to think about throughout this entire chapter, here's two of them. First of all, limit describes what happens near a point, not at a point. Okay, so as x approaches 2, I'm interested in what happens around 2, not at 2. And this is very, very important, because let's draw a little graph where things go very wrong at 2, but everything looks good around 2. So let's say I have this graph. Everything is nice and smooth outside of this one point. Let's say this is 2, and let's say this value is, 3. Okay, so the graph itself is a nice smooth function, except at 2 we have a hole. But again, if I were to compute the limit as x approaches 2 of this function, let's call it f of x, then I will be thinking, as my x's go closer and closer to 2, what do my y values approach? So you can follow this on the graph. As your graph gets closer and closer to 2, what does the y value that it approach? It doesn't actually have to equal to that value. It just has to equal it in the limit, so as it approaches it. So here we can see that it will approach 3, although it will never get to 3. And that's okay. But also notice, for example, that f of 2 here does not exist, right? There's a hole there, so the graph itself doesn't exist, but the limit value does. And the second nuance here is that for the limit to exist, the function cannot approach two different things. If the limit exists, it has to be unique. Okay, so let's draw a little graph here as well to justify this to ourselves. So here, what would the function look like if it were to approach two different values near, once again, let's say our favorite chosen number is 2. So if it were to approach something one thing on the right and a different thing on the left, so let's say my function looks like this, okay? So then let's say this number is 3, I don't know, this number is 5, okay? So then we can see that the limit as x approaches 2 from the left of my, let's call this not f, let's call this g, of g of x, and the limit as x approaches 2 from the right of g of x are going to be two different numbers. And again, think about walking along the graph. So as x approaches 2 from the left, it physically means from the left of 2. So as I am walking along the graph from the left of 2, what y value is it approaching? Well, it's approaching 3 here, right? So this limit is equal to 3. As I'm approaching 2 from the right, I'm going to walk along my graph toward 2 from the right. What y value am I approaching? 5. Okay? And this is exactly the problem. If a limit at 2 is going to exist, it cannot be 3 or 5. If it exists, it has to be a unique number. If I'm getting two different numbers on two different approaches, that means that the limit at 2 does not exist. Okay? Limit as x goes to 2 of my function g of x does not exist. Okay? We're going to see more examples of this graphically, but these are essentially things that you have to keep in mind going forward with limits. Let's take a look at how one would compute limits from a graph when you don't have a function formula, right? So a couple of examples ago, I had that y equals x squared was our function, but here all I have is a graph. Okay? I'm not going to try to come up with an equation. I'm just going to use graphical representation to come up with limits. Okay? So here, though, we're asked to compute function values and also limit values in order to see what are the possible differences. Okay? So first, g of minus 2. In fact, first, I would really like you to pause the video and try this for yourself. Okay? So pause right now and be back when I explain the answers. Excellent. I trust that you're actually good students and you've paused it. Try it for yourself. Math is not a spectator sport. You really should be working this out for yourself as well. So g of minus 2, I'm plugging in minus 2. There's my function g. So g of minus 2 is equal to 0. Now let's compute the corresponding limit here too. So limit as x goes to minus 2 of my function. So as x approaches negative 2 on the left and on the right, again, I'm going to walk along the graph, and I'm going to see that both of those points approach 0. Excellent. The next one, g of 0. Well, 0 is over here. Actually, I'm going to label this here. Okay, so g of 0, I'm going to go up on x equals 0 and look for where the function is, or where does it exist. And it exists right here. This is the filled in dot, right? This is a hole. So my g of 0 is actually equal to 1. That's where the function at 0 is computed. What about the limit as x approaches 0? Again, remember from the last slide, it doesn't matter what happens at 0. As far as the limit is concerned, it matters what happens around 0. So as x approaches 0 from the left and from the right, I'm going to follow the function from the left and from the right of 0 and see that in this case, it approaches 4. Right? It approaches this y value up here, which is in fact 4. Okay, what about g of 1? G of 1, so again, I'm going to think about where can I find the function at x equals 1, and the filled in circle is here, so g of 1 is 3. What about limit as x approaches 1 of g of x? So not at 1, but near 1. And I'm going to go from the left and from the right. And here I see that from the left, it approaches one value. And from the right, it approaches a different value. Okay? So limit here as x approaches 1 from the left is equal to 3. and limit as x approaches 1 from the right is equal to 2. Again, from the last slide, if they're not the same, the limit at 1 doesn't exist because you cannot choose, right? You cannot choose whether it approaches from left or from the right. If the limit states that it approaches that it approaches 1, and you cannot pick between 2 and 3, that means that the overall limit does not exist. Okay? And last example here, g of 2. So 2 here, there's a hole here and nothing else, which means that there's no value for g at 2. So this does not exist. Whereas the limit as x approaches 2, again, walking toward 2 from the left and from the right, we can see that the y value approaches 1. This is a very important slide here because it shows you that all things are possible. So look, in the first one, the function is 0 and the limit is 0. So the function value and the limit value could be the same. The next one, the function value is 1, but the limit is 4, which means that they could be different. The next one is the function value is 3, but the limit doesn't exist at all. And in the final one, the function value doesn't exist, but the limit does, which means all possibilities are in fact possible, right? All combinations can actually occur. So just because you know a value of a function at a point does not mean that the limit value is the same. It doesn't even mean that it exists, okay? So be very careful. If you're asked to compute it, you actually have to compute each and every case. Now let's talk a little bit more about things that do not exist, okay? So in particular limits, what can possibly go wrong and when can the limit not exist? We've already seen one important case, and that is the limit does not exist if the left and the right limits are not the same, okay? So this is going to be our very first case. That's actually, I don't have to number them. It's not like they are in any particular order. So let's say I have a function here. Again, I'm not gonna actually talk about a particular function. I just want a representation. So there, the left-hand side limit is not equal to the right-hand side limit. Okay, so limit from the left is not equal to limit from the right, which means that limit at that point does not exist. Let's call this point A. Okay, so limit as x approaches A of some function does not exist, right? And we're describing those cases. Okay, so this we also sometimes call finite jump because that's what your function does. It jumps from one point to the next immediately. If there's a finite jump, we can talk about an infinite jump as well. So this is the second case. And the infinite jump would usually be in the form of some kind of asymptote. We will discuss asymptotes in much more detail next time and actually describe them in terms of limits. But for now, we can say that this is an infinite jump, and therefore the limit here, jump, also does not exist, right? Because as you approach this value, let's say this is my A now, as you approach this value, closer and closer and closer, the function just keeps running toward infinity away from you and will never be any particular y value. Same as if the asymptotes were pointing toward negative side, okay? And the last case, this case is in some sense the most fun, but also the case we're not actually going to spend that much time talking about whatsoever, and that's the oscillating case. Okay, so here, we're not going to spend too much time talking about this because this is calculus for life sciences, and while a bunch of physical applications actually do have oscillating functions, these types of oscillating functions don't really occur in a lot of naturally described phenomenon like growth rates or anything like that. But they are interesting to look at. The idea here is that no matter how close I zoom in, the function will always be oscillating. It will never have any particular value. So we can take a quick look here at the graph, for example, of this function. It's a cosine, right? Whoops. So I can try to zoom in, but the more I zoom in, I can see that no matter how closely I zoom in, it still goes up and down. So if I fix a very particular point of x, I cannot get close enough to it and have my function stabilize. Okay? But these are the three non-existence cases that we will talk about. And next time, we will start dealing with limits a little bit more algebraically as well.